Good morning. Hello. Happy Monday. We have okay, cool. We're at 16 people. That means I'm going to start. All right. Hello, everyone. Just an FYI, I'm still making little adjustments on the grades. So, you know, I do round grades sometimes. So if you're close to a boundary, I might bump you up. Probably more likely to do that this year than other years just because of everything that's going on. But I'm still looking at that stuff. If there was an item that I missed, for example, if you did the midterm retake, I think I got everyone's midterm retake, but I'm not sure. And so if I forgot to update the midterm for you, then please let me know. If there's any other mistake, send me a Canvas message. All right. So we're on to a brand new topic. Brand new topic this semester. So we're going to start to get into electricity, magnetism, circuitry, that sort of thing. And so the first thing I want to talk about today is something called electric charge. Electric charge is typically denoted by Q. All right. And so the units of electric charge are called coulombs. Okay. Charge is basically, it's a property of matter. So you can think about it almost like mass. Electric charge is a property. It's just like an abstract property that matter has. It can be positive, it can be negative, or it can be zero. Okay. So you have probably heard about sort of the fundamental charges. Okay. So for example, there's an electron. Okay. An electron has an electric charge, so Q sub E for charge of an electron. of negative 1.6 times 10 to the minus 19 coulombs. Okay? And so that's a very small amount. So to have 1 coulomb of electric charge is actually a huge, huge amount of electric charge. An electron has a tiny negative amount of charge. And we believe that this is sort of like the fundamental amount of charge, meaning that you can't have less than this amount, okay? Or a smaller amount. The charge of a proton, Q sub p, is plus 1.6 times 10 to the minus 19 coulombs. Okay? So we don't think you could have, for example, 1 times 10 to the minus 19 coulombs, because that is, so the smallest positive amount of charge that you can have, we think, is this amount. Okay? And then there is the neutron, which has a charge of 0 coulombs. Okay, so you can have 0 charge, but the smallest positive amount of charge you can have is 1.6 times 10 to the minus 19. And in fact, so this amount right here, this is called the fundamental charge. Okay, that's the fundamental amount of charge. So so as far as we know, charge is quantized. Okay, meaning that the amount of charge, the possible amount of charges, is going to be an integer times 1.6 times 10 to the minus 19 coulombs. Okay, so you can't have 1.5 fundamental charges. You can't have 0.7 fundamental charges. You could have 20 fundamental charges. Okay, you could have negative 15 fundamental charges, but you can't have negative 7.5 fundamental charges. You get what I'm saying? So the amount of charge that an object can have is always an integer times this fundamental amount. All right? So this is like the penny. It's like you can't have less than a penny. All amounts of money are multiples of a penny, okay? At least as far as I know, you can't have multiples of or fractions of a penny. Okay? So the net charge of something, Q net, is just going to be the sum of the charges of the individual. What happened? It's going to be the sum of the charges of the individual pieces of a system. Okay? So in particular, if we think about the net charge of an atom, we would have the charge of each of the protons, the charge of each of the neutrons, the charge of each of the electrons. And generally speaking, for an atom, the net charge is 0 because you have an equal amount of protons and electrons, so they cancel each other out in terms of the net charge. If you happen to have extra electrons or not enough electrons, you have what's called an ion. Okay, so an ion is an atom that has had electrons added or removed so that it has a net electric charge. If we wanted to find the charge of U, we would do all the charge of all the protons minus the charge of all the electrons. Okay? So, because you're made up out of protons, neutrons, and electrons. there's a thing called electric current, which is denoted by I. And electric current is denoted by the amount of charge that flowed. So that could be down a wire. So if you have a wire that's carrying electricity, charge is moving down the wire. Or a lightning strike, electric charge is moving from the cloud to the ground or from the ground to a cloud. So you have an amount of charge that is flowing divided by the amount of time it took. Okay, so that is charge per time. Okay, so delta Q over delta T. So the units of electric current are going to be coulombs per second. Because it's charge per time. And so that has a special name. It's called the ampere, also known as the amp. So one of the things that electric current does when it's flowing through something is it heats it up. Because you have electric charge flowing, it's physically flowing through a medium. It's bumping into stuff, and as the electric charge bumps into stuff, it causes it to jiggle, and that jiggling is what we perceive as temperature. So if you have a breaker box, maybe outside or in the garage, you might have a breaker box, and on the breaker box there's a bunch of fuses, and on the side of the fuse it might say something like 15 amps, 15A. So that means that fuse is going to cut the flow of electric current if the amount of electric current exceeds 15 amps. Okay, for a certain amount of time. So there are fuses that are fast fuses, and there are fuses that are slow fuses. So it kind of depends on the application. So, in some cases, it's okay if the current exceeds the upper limit for a short amount of time. Okay, so you have fuses that might allow 20 amps for 1 second. Okay, so but if you go above 15 amps for more than a second, it's going to cut the flow of electric current. And then other times, if you have like really sensitive stuff, then it's going to immediately cut the flow of electric current. So there's different speeds at which fuses will trip. Okay? So that is electric charge and electric current. So really what I wanted to talk about today is something called the electric field. Okay, and so this is a really abstract concept. Okay, so let me just describe what the electric field does. Okay, so basically the electric field, it exists everywhere. Okay, so there's an electric field everywhere. It extends throughout the universe. There's an electric field. Okay. All right. Its value, the value that the electric field takes, can be different. Everywhere. So in other words, over here, you have an electric field that might be I haven't said the units yet, but the units are called newtons per coulomb. So maybe here the electric field is 8 newtons per coulomb, and here the electric field is 4 newtons per coulomb, and here the electric field is 0 newtons per coulomb. So when I say it exists everywhere, I include the places where, so electric field equals 0 still counts as an electric field being present. Okay. Okay, so there's different values of the electric field everywhere you go in the universe. Okay. Okay. And its value can be different everywhere, and also it's a vector, so its direction can be different everywhere. All right. So, over here, the electric field might point up. Over here, the electric field might point to the side. So it has different directions everywhere. So it exists everywhere. It can have a different value everywhere, and it has a different direction everywhere. The source of electric field is charge. So electric field is what is created by electric charge. Okay. So electric charge is what makes the electric field exist in the universe. If we didn't have any electric charge in the universe, then there would be no electric field. It would just be 0 everywhere. Okay. And then lastly, the electric field tells charges. Basically, it applies a force on charges. Okay, so you could think about the electric field kind of as how charges communicate with each other. All right, it's like charge A creates an electric field, charge B feels the electric field and knows how to move. Okay, so it's like a communication between two charges. One charge creates the field, the other one experiences it, and then moves in response. And every charge is feeling the electric field from all the other charges and moving in response. But then every charge is also creating its own electric field that's moving other charges. Okay, so it's symmetrical. So what we're going to do is, so the electric field is denoted by E. Okay. And in fact, if you want to sound like a physics person, you could call it not the electric field, but the E field. So that's a physics lingo for the electric field. So it's denoted by E. The units of electric field are newtons per coulomb. Okay. And there's a nice rule. Okay. For how does, so let's assume that the electric field is given. Then there's a law that tells you the electrical force that charge is going to feel. And that law is F equals QE. All right. So this is the electric field experienced by the particle. Okay, electric field experienced by the particle. And this is the charge of the particle experiencing the field. Okay, and then this is the size of the force. Okay. So in particular, neutrons aren't pushed around at all by electric fields. Why? Because neutrons have a charge of 0, and so we get however big the electric field is, it's going to be 0 times that, so there's no force. So neutrons don't move in response to electric fields. So this is our main equation for today. All right. And I want to compare it with the equation for gravitational force, which was m times g. And I want you to notice that these two equations have pretty much the exact same form. Okay? Right? Because little g is the gravitational field experienced by the particle, and m is the mass of the thing in the field. Okay? So in some sense, gravitational field and electric field are analogous to each other, and the electrical analog of mass is charge. Okay? So charge is a lot like mass. It's just a property that particles have. The only difference is that mass is going to be positive, or 0 if you're a photon. But we don't even know what a photon is yet, so don't worry about that. Okay? Mass is positive. Charge can be positive, negative, or 0. Okay? So one of the things about this is that so positive charges are pushed along the electric field. Negative charges are pushed against the electric field. Okay? So, and then if something has a charge of 0, it's not pushed at all. So let's give some examples here of how this works. What if we had an electron in a northward electric field? What is going to be the direction of the force in that case? Well, and I'm not worried about the size of the force, but just the direction of the force in this case. So if you're in a north electric field, positive charges are going to get pushed north. Negative charges, such as an electron, are going to get pushed south. Okay? So let's do another one. Let's say we had a proton in a westward electric field. So a proton is a positive charge, and positive charges get pushed along the electric field line, and the electric field points westward, so the direction of the force is going to be westward. Okay? What if we have a neutron in an upward electric field? So that's straight up into the air. Well, a neutron has an electric charge of 0. So it's going to experience no force. Okay, so that's how that works. Positive charges are pushed along the electric field. Negative charges are pushed against the electric field. All right. So let's do another example. Let's suppose that we have a charge has, let's say a particle has, let's say, minus 4 coulombs of charge. It has a mass of 7 kilograms, and it has a velocity of 10 meters per second to the right. Okay? It is in a rightward, let's say 5 newtons per coulomb electric field. What is the displacement of the particle after 3 seconds? Okay, so we'll do this problem in stages. Okay, so the first thing we want to do is we want to figure out what is the force on this particle. Okay. So the force is going to be QE. Now the electric field is to the right, so the electric field is a positive number. So we have plus 5. And then the charge is a negative number, minus 4. So that's a force of negative 20 newtons. Okay. Now, let's assume that this is the only force acting on the particle. So now we go to Newton's second law. So we have net force equals ma. And once again, assuming that this is the only force, so that is indeed the net force. Okay. We have net force equals negative 20, and that equals ma. So that is 7a, because the mass is 7 kilograms. Dividing both sides by 7, that says that the acceleration is negative, 2.86? Yeah, negative 2.9 meters per second squared. Okay, so now if you think about this, it becomes a kinematics problem. So we have the acceleration is negative 2.9 meters per second squared. We have that the initial velocity is 10 meters per second to the right. We have that the time elapsed is 3 seconds. And we want to know what is the displacement. Okay, so there's a kinematics equation that connects all 4 of those variables. It's delta x equals v naught t plus 1/2 at squared. All right, so now I just plug in numbers. I have 10 times 3 plus 1/2 times negative 2.9 times 3 squared. And we get it's about plus 17 meters. So that's the way it works. We use, if you have an electric field, you use the electric field to calculate the force. Okay, so let me write this down. The electric field allows you to calculate the force, which allows you to calculate the acceleration through Newton's second law, which allows you to predict the motion using kinematics. Okay? We are assuming that the electric field is given. This class does not teach you how to calculate the electric field. If you take the second year of physics, we learn how to actually calculate the electric field. But for this class, we're just going to assume that, someone says what the electric field is. All right? So that's my lesson for today, and I will see you in the Zoom room.